In this video, I'm going to trace the execution of breadth-first search. So this is from question 1 in the week 7 tutorial. And as we can see over here on the right-hand side of the screen, this is the graph that we're going to be operating on. So if we scroll down a little bit, let's just take a look at the implementation for breadth-first search first. So to run a breadth-first search, you need to set up some data structures before you actually do it. We need a visit data structure. In this situation, we are making an array of booleans, so there'll be true, false. We need a predecessor array, and this is going to store integers. Basically, this is going to keep track of the previous vertex that you came from as you're moving around. And we also need a queue. Queues are first in, first out data structures, and this is the ordering that we need to maintain if we're doing a breadth-first search. Depth-first search, which we'll see in the next video, is a bit different. But yeah, just keep in mind, if we want to do a breadth-first pattern of visitation, we need a queue. So before we actually start moving around the graph, we just need to initialize our data structures. So basically, the first move you make in a breadth-first search is you set the source node to be visited. So what usually happens is you'll get given a function like this. The user has to provide some source vertex from where to start the search. So yep, we set that to be visited, and we also put that node into the queue. This basically kickstarts the algorithm, because if we look at the next line, we can see this while loop. This is the thing that's driving the traversal. That's like moving you from vertex to vertex. And for this loop to work, you've got to make sure that the queue is not empty. So this initialization step is essential. So let's just look to the left-hand side of the screen for a moment. What we're going to be doing is updating these data structures each time we move to a new vertex. So up here in round 0, you can see that I've already put some values in. These are just representing that initialization step I was just talking about. So I put 0 into the queue. This is my visited array here. I've set index 0 to be number 1. That's just going to stand for true. So we've visited node 0. And in the predecessor array, I've got -1 up here at the 0 position. Basically, with the source node, there is no predecessor. That's the starting point. So a common way you will see this represented is you'll just have a -1 to represent that. Okay, cool. So yeah, this round 0 it's just representing this bit up here. So what happens after we finish that part of the code? We essentially come into this loop down here, and you can see there's a bunch of stuff happening. First of all, you just take whatever's off the front of the queue. You can think of this as moving on to an actual vertex. There's a bit of a blank space here. This is sort of where you would do whatever operation you need to. It'll depend on what the question is that they ask you. In this question, we're just printing the number of the vertex out to the screen. But in an exam, they could ask you to do anything there. It really depends. But yeah, we're just going to print it to the screen, and just flipping over back to the left-hand side of the screen. That's why we've got this print column over here. So print. In this column, we're just going to write, okay, in like round 2, for example, what vertex did we print out with this statement over here? After that, we've got this loop, and this is the bit that's looking at the neighbors. So to make your breadth-first search work properly, you have to do 2 things. You have to visit nodes, like you actually have to step onto the vertex. But then once you're there, you have to look at the neighbors and then put those into the queue. Because once you've finished visiting the one that you've just dequeued, you then have to go and visit the neighbors. So that's what this loop is doing down here. So because, oh, and also this is going to be, we're representing our graph as an adjacency matrix, so we can see that on the left over here as well. So this loop is basically just scanning across one row of the adjacency matrix. This if statement contains two checks that you need to make for each vertex. If vertex W is a valid neighbor of the node that you're currently standing on, it means that this must be true. This is checking the adjacency matrix. So if we find the number 1 at these coordinates, it means that there is an edge that we can travel along. But also you must not have visited that node before. So don't forget when you're doing graph traversals, there's always these two checks you have to make, at least. Sometimes there's more depending on what you're doing, but these are the two basic ones. You always have to make sure there's an edge between you and the vertex you want to travel to, and you also can't have visited that vertex in the past, because these traversal algorithms, you don't revisit nodes, you only revisit vertices, sorry, not nodes, one time at a maximum. Okay, cool, so that was just a quick overview. So let's go over here to the left and do the actual trace of the breadth-first search. And let's say that the user gave us 0 as the source node. So we're going to start on 0. So I've already done round 0. So let's, okay, so we're visiting, well, we're currently standing on vertex 0. And so yeah, we're in the loop. So the first thing we do is we dequeue 0 from the queue. Then we're going to print out 0 to the screen. So over here in round 1, we print 0 to the screen. That's the only operation we have to do. So now we can just move straight on to looking at neighbors. So let's go over to the adjacency matrix. Since we're standing on vertex 0, we're simply going to scan across this top row of the adjacency matrix. Each time we find the number 1, we then go and check the visited data structure. And if we haven't visited it, then we can go ahead and put it into the queue so we can visit it later. Okay, so there's a number 1 here, which corresponds to vertex 1. Let's go to the visited data structure. We'll look at the 1 index. That's a 0. That means that we haven't visited 1 yet. So if we find one that we haven't visited, we mark it as visited, and then we put it into the queue. So now we've got the number 1 in the queue. Oh, but we've also visited 0, so let's put that there too. So yeah, we put 1 into the queue, but don't forget there's also 2 other things you have to do. At the same time that you're putting neighbors into the queue, you have to set them to be visited. Oh, yep, so that's what I already did. But the other thing is you have to set the predecessor. So if we're standing on vertex 0 and we're going to travel to vertex 1, it means that the predecessor of vertex number 1 is 0. So we go to the first index of the predecessor array and we put 0. Cool. Now, there's also a bunch of other ones along this top row, so we do the same thing for all of those. There's one for vertex 2, so we can put 2 in the queue, and then we put 5, 6, 7 in the queue. And at the same time, we need to mark all of these ones as visited. So what have we got? 0, 1, 2, 5, 6, 7. And we also have to set the predecessor for those vertices to be 0. So 0, 1, 2, 5, 6, and 7. So after round 1, this is what the data structures look like. We've almost used the full graph. There's only 3 and 4 that we haven't looked at so far, so everything's in the queue at this point. Okay, so that's one round of breadth-first search done. So in terms of the code, you'd be down here at this bottom brace down here. We go back up to the top of the while loop. We check the queue is not empty. It obviously isn't. We have like 5 things in there. So we come into the loop again, and we simply take whatever is on the front of the queue, which in this case is going to be vertex number 1. So we dequeue 1, we print the number 1 to the screen, and just like before, now we start looking at the neighbors. So we'll go down to the adjacency matrix. This time we're looking at row 1. And we can see on row 1, we find there's 2 edges, one to vertex 0 and one to vertex 7. Now, vertex 0, yeah, it's true, there's an edge, but if we look at the visited data structure, we've already visited that one. So that means we are basically just going to ignore this one. When we get over here to vertex 7, it's the same deal. There's an edge between 1 and 7, but we've already set it to be visited. We can see up here, index 7 is 1. We already set 1 to be visited when we were standing on vertex 0. So we just skip that one as well. Over here on the right-hand side of the screen, it's this if statement. Basically this not visited thing. That's what stopped me updating my queue and my other data structures when I was looking at the neighbors of 1, because I already did them when I was standing on vertex 0. So there's not really going to be any changes here. So let's put 0, 0. And all of the visited should be the same. I'll just grab the queue while I'm here. So let's get all this. Okay. Now the queue is going to be slightly different because we're visiting vertex 1 right now. That means we must have dequeued 1. Okay, cool. Right, so that's the second round of breadth first search. Like I said before, we'd be down at the bottom brace down here of the while loop, come back around, check if the queue is empty. If it's not, we go ahead and dequeue the next thing. The next thing is going to be the number 2. So let's just put a star up here to signify we're looking at vertex 2. Now once we've printed 2 to the screen, we're going to check our neighbors. So let's go to row 2 of the adjacency matrix, and we can see there's only one edge in this whole row. Vertex 2 only has a connection to vertex 0. And similar to like what we were saying about vertex 1 a second ago, we ignore this one because we've already visited vertex 0. So again, nothing's going to change here. So how about we copy paste all of this. At this point, 2 will not be in the queue because we just dequeued it. Alright, that's the third round of breadth first search. So just like before, we're going to come around and first of all check if the queue is empty. If it's not, grab the first thing. In this instance, it's the number 5. We get that off the front. Now I might just copy paste all of this. Okay, now when we get to vertex number 5, it's a little bit more interesting. If we look at the row that corresponds to vertex 5, we can see there's 3 edges. There's an edge to vertex 0. This one is the same as the others. We've already visited 0, so we skip that one. But 3, like column 3 and column 4, means there's edges between vertex 5 and 3 and 4. We have not seen vertex 3 or 4 yet, so that means our data structures will change. So if we scan across this row, we get to vertex 3, we check the visited data structure 0, 1, 2, 3. We can see it's currently 0. Now we're going to set that to 1. And at the same time, we're going to put 3 into the queue. And we need to set the predecessor of 3, 0, 1, 2, 3, which is this one. The predecessor of 3 is now going to be 5. We're currently standing on vertex 5, and we're evaluating vertex 3 to see if it's a valid neighbor. It definitely is, so if we travel there, it means we must have come from vertex 5. Cool, and then the same thing for vertex 4. So we put vertex 4 in the queue, set 4 as visited, and the predecessor for 4 is going to be 5 as well, for the same reasons that we used 5 for the predecessor of 3. Cool, so that's the 4th round of breadth first search. Oh, whoops, we dequeued 5, so 5 is not in the queue anymore. So let's go ahead to round 5. We'll be printing 6 to the screen because that's the one at the front of the queue. Now, since we have basically set all of the nodes to visited already, any sort of like neighbor checking or anything like that that we do now is never going to change any of these data structures. So we can pretty much just copy paste this stuff. So we need 6 out of there at that point. Great. But just for illustration, when we dequeued 6, we would have went ahead and printed it to the screen and then gone to the 6th, or the row of the adjacency matrix that corresponds to vertex 6. We would have found 3 edges, 1 to 0, 1 to 4, and 1 to 7. But all of those have already been set to visited, so none of these data structures will change. But this scanning of the rows still happens. Just keep that in mind. Doesn't really change any of the values, but it impacts the time complexity. Cool, so that's round 5. The next round we're going to grab number 7 because it is at the front of the queue now. Let's copy paste this. Okay, 7 is not in the queue. Great, so we just visited 7. Oh, I missed my 6. We've already visited 6 as well. And at this point, you can kind of see the breadth first search pattern. The idea with a breadth first search is that you visit the nodes that are closer to the source before you visit the ones that are further away. So currently we've visited 0, 1, 2, 5, 6, and 7. They're all the vertices that are 1 edge away from the source. Now as we move into round 7, 3 is on the front of the queue, so we'll get 3. You can see that we've started visiting the nodes, or vertices, pardon me, that are 2 steps away from the source. So 3 and 4, it doesn't matter which way you look at it, the minimum distance from the source to both of these nodes is 2. 0 to 5 to 3. That's 2 edges. 0 to 5 to 4, that's 2 edges. With a different pattern of visitation, you could also go like 0 to 6 to 4, or 0 to 7 to 4. But either way, we're visiting 3 and 4 after we visit the nodes that are 1 edge away from the source. That's the point. Cool, so there's just one more thing left in the queue, the number 4. Say it's empty. We print 4 to the screen. We do our neighbor checking, going across this row of the adjacency matrix, but just like before, we visited everything, so we don't add anything back to the queue. So that means the next time we come around and check if the queue is empty, now this is actually going to be true. Because we've got the not operator out the front, it becomes false. This whole statement together becomes false, and this loop will end. And that basically ends our breadth first search.